Thank you, Sujan. Hi, everyone. Today we're going to talk about a kind of interesting research direction on the RAG systems, but I will try to keep it as applied as possible. And though I'm assuming that most of the people over here are technically in depth, but we will also try to talk about high-level concepts as much as needed so that we can also understand the technical details. So in general, what is retrieval augmented generation? Probably everyone has heard about that, where we will have our LLMs that we would need to provide access to external data sources. So during the search time, we will try to find the corresponding context from our documents, from our databases, etc., feed it into the LLM so that we will, at the end of the day, get an enriched answer using this external context. This is like the very simple overview of what is RAG. And for preparing a RAG application, one is to, of course, first of all, solve the data ingestion, which is you can have lots of different documents. You need to load them, consolidate. You can have various sources. You need to process them because computers themselves are not, or neural networks are not ready to read it as a text. You need to somehow process it. The way that we process this is called chunking, where we will create vectors that kind of represent the semantic meaning. And this is just high-level overview. It's not the main part of our topic. This is just an overview of a regular RAG pipeline. And when I say regular, what I mean is that during this ingestion, the most difficult and important part probably is this parsing and extraction, where you will have different types of PDFs, where you can have various charts, tables, images, you name it. And those are not standard texts, and it's not easy to extract, process, and fit to your LLM. Especially if you have financial reports, dashboards, any kind of charts, it's very difficult to process them before your application is ready. So this is the kind of bottleneck that usually the regular RAG system face. That's why today's talk we will go and explore the visual RAG, and we will talk about that a bit later. So a bit recap on the regular RAG. So let's say you have a regular PDF document. You need to do a couple of processing steps, such as the OCR, optical character recognition, that you can kind of extract the text from the PDFs, let's say, but this is just an example. You can have hundreds of different types of documents. Then you might probably need also some layout detection, which means like you divide semantically, like whether it's a paragraphs, I don't know, subpoints, subsections that can be very important to your LLM. Let's say you have a table. The simplest thing you can do is with some indentation, you can just create this textual representation of that same table, but it means you need a rigorous processing to understand that underlying structure, the layout. And there are plenty of tools in open source, say the same DocLink, which provides you free access to such tools that provide those kind of processing. But the problem is that you can lose different types of data, whether it's charts, images. Of course, you can go deep, and for instance, many people do the following. They take an image from the PDF, they use some LLM to describe this image and use this small text as a description. But again, you are losing some data. Besides, these take lots of time. According to some estimates, let's say you are using some hybrid strategies that we talked, like using LLMs, etc. Through DocLink, one PDF page to process can take 7 to 8 seconds. And imagine you have thousands of documents, thousands of pages. So again, this is both computationally expensive and does not guarantee you the highest performance. So at the end of the day, we process, and after processing, we do the chunking, after which we get a representation for the text chunks in the face of embeddings, which we store in the vector database. That's a whole another story. But the important part I wanted to emphasize, or this is the bottleneck that we have during this regular text pipeline, text processing pipeline. And a bit like a background for us on the transition to the visual RAG. So everyone heard of transformers, and they got very famous with NLP in the NLP field. But as time passes, people realize that, okay, these transformers are doing a great job. Why wouldn't we try to use them in other fields, such as computer vision? And very first steps in this field was the visual vision transformers, where in compared to regular transformers, which divides text into tokens, probably most of you heard, the same token usage that you all oversee in OpenAI Cloud that you use, that's about the same tokens. This is how the model gets the input. So in Vision Transformer, what it does, it has an image as an input, so there's like not a token concept. It's not like symbols, it's not like characters, no words. So what they do, they just divide the image into patches, like this, and consider like each page of this image as a separate token, and they process it. That's like a whole another story, but the point was that this is the background for you. Like there are visual transformer models that understands these type of tokens. Like they divide image into patches. And with this in mind, what happens is that now we have models that can basically mimic the human eye. Like they can see this image text, they can read, they can have understanding of these charts. Due to which people start to realize that wait a moment, why we would use the previous text pipeline if we can try to use the same vision transformers under the hood to process our regular documents that are actually kind of text-based but have lots of visual components in it. So the proposal came with a very interesting paper. I highly suggest to read the Kolpali paper. In a couple of words, they proposed a model that does this for us. So what they do, they again divide the image into different patches, process it with their encoders. And today we are not going to go deep into any kind of model architecture. And most of you probably wouldn't even need to tweak or fine-tune these models, but just to you for understanding that there are these approaches, and you can just use these models inference time. And putting things simple, like they provide representation per patch. So let's say they divide the image into 1,000 small patches. It means for one page, these vision models provide 1,000 embeddings. This is how they describe what's in the image. This is a representation. And in contrast to the regular one, where we can see that per text chunk, we will get one embedding. And usually, I don't know, one PDF page is like 3 to 4 chunks. So 3 to 4 big vectors that represents your page. Versus in this pipeline, we would have thousands of vectors, but small vectors. The dimensionality is 128. We will talk about that later. So in this approach, we are extending the number of vectors representing the same page. And you might think that this is not optimal, and we'll talk about that later, but this improves the performance. And they showed in their paper in many benchmarks that they managed to achieve from, 66% to 81 on the famous NDCG score, normalized document cumulative gain. And during search time, what happens? You have some query. Each of them is getting processed. You get the query tokens. And now, per document, there are thousands of vectors. For each query, it does the attention and then tries to maximize over the query axis and finds the most relative vector over this 1,000 patches. And in the later sites, it will be much easier probably to see. And just takes over the same max similarity score. And this is proven to yield better results. But as you can guess, the next topic of our discussion will be this huge amount of vectors that will become a problem once we would like to scale this visual RAG system. And our work proposes a couple of optimizations, and we will go on all of these axes, let's say this way. First is token cleanup. So usually you will have pages that have lots of empty spaces, empty blanks, right? Blank spaces, parts. And because of this, you are losing some patch tokens. This just has no contribution at all. But if you process your image as it is, you are just spending up some extra tokens. This is just the very first sample. And most of the vision models that are out there are tons of different types of Kolpali alternatives over there. And since this visual RAG became a thing, everyone started to produce their own models. So there are lots of powerful Qwen family of models, and each of them has their own specific processing. So let's say there are different images, you cannot pre-guess the input size. It means you need specific processing for that. And under the hood, each model has its own processor, which has its own, let's say, business logic that can resize the image according to the input size that the model is trained for. It means your image at the end of the day will eventually be resized according to its model's processor's requirements. So a good thing would be to initially crop the parts which are not necessary. This is like very simple thing before the resize, so that in the resize you will also have a bit zoomed out all this text and other elements, which also improves the performance. These are just some examples, and also imagine that you can have, I don't know, a page number over here. Most of the documents have a page number somewhere around here. So because of, so what you can do, most of the time you are not interested in the page number when you would like to encode this text, to process this text, so you can eliminate it, be very aggressive, and eventually lots of parts of this single page are not useful. And there are different types of experiments you can run yourself, try to do aggressive cropping or just a regular one. But in the end of the day, it's just a good optimization because it will save you some tokens and will also improve the performance. The next thing that I would like to mention is some of the special tokens. So most of you, if you have encountered with any transformer-based models, you might have seen some weird tokens like, I don't know, some, or BERT models, some CLS tokens, some, I don't know, starting token, end token, separation token. In BERT, for example, you are training with 2 pairs of sentences, and between them you have another token. So these are some special tokens, and given the model, you can have different types of tokens. And these are not useful most of the time for our RAG task. Even more. There is the CLS token, one of the most famous one. If you can recall from BERT paper, the famous encoder, CLS is it's a token that kind of summarizes the whole sequence of tokens. So if you have a sentence, the first token you will have is, let's say, the CLS token, and for each token in that sentence, you will have separate embedding. So most of the time, the CLS is kind of an aggregated representation, which people mostly use during classification tasks. Like they will get some transformer model, process the input, but they will just eliminate all the other token embeddings and just take the CLS token. And in our case, this actually will hurt the performance because it will just have some aggregated meaning and will prevent the max similarity score that's usually applied during the semantic search to be correctly matching the corresponding context based on the query. So what we do, we just track these special global tokens and disregard them. We don't use them during our search time. And also another example is when these models get their input, like you provide the image and get an embedding representation. They are multimodal most of the time. They have text encoder, they have separate vision encoder, and most of the time input to them is something like this, where you will have your image tokens. These are these patches that we talked earlier, and you will also have some text like describe this image. This is also a necessary part which can save up you some tokens. And at the end of the day, with these small optimizations as well, we are in the paper we showed that there are some good improvements. Sorry, I've forgotten to say that whatever we are discussing here is already accepted published paper in SIGIR. It's like the top 1 conference in the world in the field of information retrieval. Continuing on these optimizations. How we have already talked about the CLS, same with the padding token. So there are lots of places where you can go deeper, but just a high level recap is we have lots of tokens that we don't need, so we just try to track and optimize the number of visual tokens that we create, so that both the performance and the speed during search time will be improved. But and this is like just arbitrary example of whenever you have this CLS token that can kind of hurt the performance because it takes on itself most of the similarity score, and because of this, whenever you strip this CLS token, then some keywords in your query, let's say you have a document about some financial report and your query asks like, what's the most challenging part of this fiscal year, something and something. So this fiscal year and a couple of keywords can actually point to correct documents, but because of some representative tokens, which can you can have a smooth out distribution of this similarity scores, and eventually you will miss the good matches, and instead of this inflated tokens. So spatial and global tokens like this we just eliminate. Next thing that we are going to talk is the another axis of optimization, and for that we will go through a bit recap or overview. So we have a page. This is the raw input. Then we will have some resize based on the processor. And this is a real example when before the model gets its input, it divides this image into 4 rows and 3 columns, not intersecting patches of image. Then it also squeezed the same image into a smaller dimension, 512. This is like a global representation of this context, because when you split like this, what if you have a paragraph that's going from here to here? So you can lose some context. So it also compresses the original image as a global representation. And for each of these patches, this is the call small model. This is just example. We are using this model to illustrate the idea. So what it does, for each of these patches, it creates 8/8 small inner, so this is a bit technical, 8/8 smaller patches, and for each of them it gets an embedding representation. And at the end of the day, for this page, the original page, it gets 832 embeddings with this dimension, this size. Call Poly model will provide always this type of grid sizes. We will see that later. And eventually it will provide 1024 if we remove these extra tokens. Otherwise it will be 1030 something. So having this in mind, what's our idea is to reduce this matrix. If we can decrease this matrix size, it means we will optimize our future pipeline when the number of documents would get, I don't know, thousands or millions. And we can do this 2 ways, right? We can either decrease the dimension of these vectors, or we can decrease the number of vectors. Like, literally, very simple. And let's talk about both of these approaches. For the first approach, there is actually a very good studies on decreasing the dimensionality. Probably most of you have encountered the idea of dimensionality reduction, whether through PCA or other algorithms. In this particular case, there is a famous strategy for during the regular text RAG systems, text-based RAG system, that's called Matryoshka. Matryoshka is this Russian doll that you have the same toy, but in different sizes, one inserted in another. So motivated by Matryoshka, people started to do the following. They are training the embeddings in a way that most of the important information is within the first pixels, first part of the embedding, which means if you divide your overall embedding in half, for example, you will still have a very good representation of your semantics. So these are specially trained embedding models, which help you to decrease the embedding sizes very easily without any external training, without any completion algorithms. It's just you have a big embedding. So if you have your computational resources, just use this big one. But if you have lower computational resources or you want to optimize for scale, you just take the first X amount of pixels of coordinates in that vector. But in our case, the problem is that we already have very small embeddings. And if you decrease it, it's like we already have a golden ratio. It's like both representative, it provides a good performance. This is state-of-the-art RAG systems, but it's already small. So if we go even smaller direction, it will significantly degrade our performance. So going to this direction will be much more difficult than trying to explore the second approach, which was decreasing the number of vectors, right? And very briefly, just a quick recap. This same idea you have probably encountered, for instance, during convolutional neural networks, if you have studied those, where you have the idea of pooling. Like you have some representation, some feature map, that happens during the middle layers of some convolutional neural network that represents the internal state of the image or whatever your model is trained for. And you do some pooling that you have a couple of, I don't know, points, and you reduce it to 1 point. So in this case, instead of this 4, you are just having this one. So you just this is not a direct way of dimensionality reduction, but in general, this is what we're going to do. That's why I'm preparing this context recap. There are different types of places when pooling might occur. This is just another easy example where you would have some geographic data, you have lots of points, and very simple aggregation when you start to aggregate points based on, I don't know, some latitude, longitude range, based on the, in this case, how deep is the water, and you start to aggregate by groups like greater than 3 kilometers, from 1 kilometer to 2 kilometers. So you start to kind of do some poolings, max pooling, whether average pooling. This helps you to decrease the number of, let's say, points that you need to store, while preserving some semantics, right? And this is a proven approach because before this transformer, vision transformers, we all know that these convolutional neural networks were working pretty good in computer vision tasks. So what we thought is to use some pooling over this matrix of vectors that represents our image. So instead of this big matrix, we would do some pooling. And before showing the way that we pool, like a very common thing to recap. So what's a kernel? Kernel is like, there are different types of kernels in machine learning. In this particular case, it's like a sliding window when you can apply over vectors, over matrices, doesn't matter. And in this particular case, in your kernel, you will have some weights. This is how people usually call them, right? Like coefficients. So whenever you slide over, that can be used, I don't know, in time series forecasting, when you try to go over some time series data and you do some aggregations, moving averages, doesn't matter. Many people use these sliding windows. So the regular average that all we know from basic calculus from our schools is you take the average of all the numbers by summing up everything and dividing by n. This is the same idea as if you had a kernel with weights like 1 over n, right? So uniform is like provides you uniform kernel. If you slice it as something over this uniform kernel, it's the same operation as if you just take the mean. Like we will talk about that. And there are some couple other ways so that instead of uniform, we can put some other types of weights. And we'll talk about this, like how we do it. So this case study is over the cold poly. This is what we did. So we have an image. Cold poly processes it into 32 over 32 patches. This is how it works. And for each of them, it processes and provides a 128-dimensional vector. So what we want, we don't want to store all these 1024 vectors. So what we do, a simple approach, we just take all this stuff, this row, and just calculate its average, like very simple, right? This is the uniform kernel. You can consider thought of this as a uniform kernel applied. And by doing this, we'll just decrease the number of vectors as from 1000 to just 32. Another thing is to then do the benchmark and prove that this does not hurt the performance, which we of course did. But anyways, this is just the simple formula, a fancy way of saying that this is just the average over the row. And this is for cold poly. So if you can recall, I've already told that given the model, the processing that it has trained with is different. So one of the limitations, I will already give you the spoiler, one of the limitations of our work is that for each of the models, one might need to implement the strategy for pooling. So though this pooling strategy, so we don't need to train anything. It's just you will need to come up with the correct way of doing this pooling. But so the good thing is that it's training free. You don't need to do any fine tuning, any training, but given the model, you might need to adjust the way that you do this pooling. So another approach is for, this is for example, for the cold small model, which instead of 32 over 32 does something like this with this global representation. So for instance, cold poly does not have the global representation. So these are two separate models doing the same thing. Given the image, they provide you different vectors that represent this image, but the underlying processing that these models use is totally different. So that's why our pooling methodologies is also adjusted based on the model. And coming back, this is for that cold small model which was using these tiles. And for these tiles, one can do a pooling over this tile instead of a row. I'm just trying to keep things simple, but at the end of the day, most of the time we used either triangular or Gaussian kernels. And I don't want to go deep into the mathematics or how this works, but in general, you can just imagine the same pooling that we were talking all over again is applied, but just instead of uniform weights, we are using some underlying other distributions to construct these weights. And in the paper, which this presentation is based on, there is all the intuition related to for which model, why we use the particular one. But for example, I will try to provide for one of the models. So this is the Cole-Pally and Cole-Quen. So for Cole-Pally, we have already talked. The Cole-Pally is this one. It divides any image into 32 over 32 patches. For this Cole-Pally, it's very easy to just use the existing simple row averaging. Why? Because all these patches are disconnected. They don't share any, they are not overlapping patches, and the underlying model that operates over them, in contrast to, it will be easier to put it this way, in contrast to this Cole-Quen, which has an internal patch merger. It's like if you go and investigate their code in the architecture, you will see they have a separate model called patch merger, which for some reason their model has a pooling or merging layer module on its own. So it means you will perform average over average, which kind of messes up everything, doesn't make sense at all. So that's why for Cole-Quen, we didn't do the regular average, but we emphasized the central row within this average group, where during this triangular, the central one has more weight than the neighboring ones. So again, for fully capturing this one is to go a bit deeper into the model architecture of the specific models and their processing. But high level is, given the differences of these models, we made our choices on which distribution to use when selecting the weights of the kernels. So we have talked so far about, okay, we have this visual RAG, it provides better performance, but we have lots of vectors, and we talked about how we can reduce this number of vectors. But of course, okay, we reduce the number of vectors, what then happens to the performance? Like, initial goal was to improve the RAG systems because we couldn't process the tables, charts, etc. in regular PDFs. So we used Visual 1 to improve the performance, but now we might actually negatively impact the performance, the quality of our system. So to address this, another conceptual recap. So I don't know if you are familiar with the re-ranking strategy. It's a strategy that's mostly used in modern recommendation systems, search engines, the same Instagram that you all over scroll, or YouTube recommendations. Mostly they are pipeline where, I don't know, you go to YouTube, there are billions of, I don't know, items, right? Music, whatever. And within seconds, it finds you relative ones. In a couple of words, first, it has a big catalog. It tries very simple processing, like, I don't know, using your information, your geographic information, very simple features to narrow down from billion items to, I don't know, 10,000 items. Then it uses more advanced models, which is computationally more expensive, so that it first decreased the number of candidates. But now, at each stage, it uses a more powerful model over less number of candidates. And at the end of the day, with this couple of stages, 2 or 3 stages, it will get you your recommendations. So this re-ranking is the following. So initially you will have X number of documents, chunks, whatever you name it. And this can be in scale of, I don't know, millions. So if you have a very powerful model that does this similarity search, it will take you lots of time to try all over these items and then compare which one yields the best result. It's like, if you have infinite resources, that's fine. But most of the time, when you have, I don't know, production systems, you have sub, I don't know, 0.5 second latency SLAs, and you can't operate over all these samples. What you do, you use a light model or light strategy, simple features, it doesn't matter whether the model is a simpler model or the input is not complicated a set of features. You just try to narrow down the number of candidates, and then from the very big asset, you narrow it down, and then you use a more powerful model to re-rank them. Because this more powerful model is like your last chance of fixing everything that you could have done wrongly in this first initial step. Because this initial step is just to reduce, to provide you a good set of candidates, but the next one is to provide you the perfect set of candidates with the correct rank. Because most of the time, you just don't need to, you're not only caring about extracting or retrieving the good candidates, you also need to rank them according to the observed relevance. So for example, if you search something in Google, most of the time you will click the first, second, or the third result. You probably won't go all over, scroll, and select the 10th, or I don't know, go to the second page. So even having them placed in the correct rank is also important. And the same with LLMs. Whenever you provide LLMs lots of chunks, lots of context, most of the time it will remember the first couple of ones and the last couple of ones. In the middle, it gets lost. So this ranking is very important. And in our case, we will talk how we will do this first stage and second stage. Everything will become much cleaner. And before talking about this re-ranking in our study, just a very quick recap. So most of the time, the vector databases where all these vectors are stored are based on some very advanced data structures. One of the most famous ones is this hierarchical navigable small words, which you can imagine as some graph within a couple of floors. I don't know how to put it in a simple way. Just something like this you can imagine, which is a pre-processing step. So you have lots of vectors. You construct this graph. This is a one-time job, but it's very expensive. So once this graph is constructed, where you will say like your data is indexed. Like in regular software engineers do, like they have their own databases and they do these different types of indexes, right, over their columns. In our case, in AI, we have this embedding indexes, let's say. That is just an example. And the idea is that this helps during the search to do very quick graph traversals. So if you have millions of embeddings and user asks something, instead of you comparing against all these 1 million vectors, it just helps you to kind of pass and compare to the most relative ones. Because the way that this graph is constructed, like neighbors are mostly connected. But this is, again, very advanced topic. If we go deep, just the idea was that, let's recap that, okay, our databases use this one-time indexing for building this data structure. And this, again, if you have thousands of embeddings per document page, and you have many documents, each has, I don't know, 500 pages, then even constructing this one and then updating it will be a really big headache. So let's say you have a system where, I don't know, in university, new exams, new topics, new quizzes, you have all over the time, you have some new data incoming, so you need, I don't know, to weekly update your database. So updating this one with millions of documents is not the, not the task that you would love to do if you have these millions of vectors all over there. So having this thing in mind, what we will talk about is how much we optimize both the index construction and the search time. So most of the time what happens, we have some query. This query is being processed and for, I don't know, in regular English, I don't know, one sentence is mostly, I don't know, 8 to 10 tokens. So for each token, one would go to each document in our database. For each document, right, you will have n number of embeddings. So for ColdPal, initially we had 1,024 embeddings, right? So it means for all this, for one query, it will go like over here. Let me go scroll all the way up to the computation. So for one query token, in this case we have 3, let's say, it will go take, let's say, one particular document. For that document, there are 1,000 embeddings. So it will compare, and when I say compare, it's just cosine similarity, right? It will do this dot product with the query embedding of this one over all these vectors for this particular, let's say, document. And when I say document, it's like this, 1,024 embeddings. And this is just a single image. It needs to do the same for all others, right? So computationally, you have over here number of query tokens, number of documents. Per document, you have number of vectors. Each vector is, in our case, 128 dimensional. It can be different given your model spec. So this is the number of operations you need to perform for just one retrieval. And what we do with our optimization, we manage to decrease the number of vectors, and we decrease it so significantly that in our case, let's say from 1024 we get to 32. It gives us quadratic time optimization. And if we also consider the index build time, but it's actually, let's not go deep into how it's derived. Putting things simple, if we continue to use our pooled representations, so whenever we talked about pooling, so let's say 32 vectors instead of 1024, and we will also embed those small sized matrix representation of this. It means during both index construction time and the search time, we will have very big optimization, very big latency improvement. Now the only thing is about the quality. And during this quality issue, this is where the re-ranking comes. And in our case, we have already talked that we are storing both the regular, we have this original set of vectors like 1024, and we have obtained a lighter representation of it. So this should have remind you the context that we gave about this re-ranking. When in the first stage, you are using some simple strategy to narrow down the list of candidates that you have, and then you will use some more powerful technique to rank them. So in our case, this first stage can be done using these pooled representations that we calculated, right? So for this first stage, we will have our vectors, pooled vectors, which we already have the indexed data structure in the vector database, which is much faster compared to if we would construct this index over the initial set of vectors. So this operation will be much faster. So we will have, let's say, 256, 512 candidates using the pooled representation vectors. And then what we can do, we can go back and take their initial vectors, that all 1000 ones. But just for this small sample of vectors, and do the re-ranking using their initial, more rich representative vector representations. And by doing this two-stage re-ranking, so instead of going and doing a regular one where we would use the all the vectors without any pooling, etc., with one stage, versus if we do this two-stage retrieval with this re-ranking, eventually it comes down that we managed to, in our case study, we managed to do around 4 times faster with almost negligible performance degradation. So again, this, I don't know, can you see the numbers? It's basically for one document. This is the vector database, screenshot taken from our vector database. We have lots of different vectors stored. But computation time, we are, so again, you can do different types of poolings. We have talked about that. So we have different types of representations for a particular image. And you can play around, of course. You can use different types for the first stage, then second stage. If you want, you can go even deep and do some three-stage retrieval. Again, it's all up to you. We have created a Python package, so you can also play around. We'll show that in the later slides. So, a basic example, okay, let's do prefetch using the pooled vectors, 32 vectors per page. Already indexed and cheap operation. Narrow down to 256 candidates versus, I don't know, millions of candidates. And then use their initial 1024 vector representation to narrow down to just 10. That's what we did. And the corpus that we used is actually very small. That's why we just had 4 times faster. But I believe if we can scale to millions of documents, so let's say, I don't know, for a much bigger project, the performance would be even higher. But this is just one sample of the table in our studies. And in words, we can see that most of the time, production systems don't go beyond 10, or I don't know, maybe 20. And for this most important 2 metrics, probably, we have almost no degradation in performance. So first stage is the regular benchmark that we have. Like if we didn't do all these optimizations, it means we would go with the first stage regular retrieval. So this is what we compare against, these first stages. And we did this comparison of all these 3 different models because each of them is different in terms of how they do the processing. And we showed that almost no degradation except for the smallest model out there. For the smallest one, we can see a bigger degradation. And this is like a future work mentioned in our paper, is that we believe that up to some point, the models are not capable enough to perform well with the pooled representations. So their initial set of representations, the vectors, are not so rich that even after pooling, they will remain very meaningful. And this is just, even the name says, this is like 500 million parameter model, while the others are around 3 billion. So after some threshold, which can be found during the future work, more capable models are totally fine with these optimization strategies that we have talked so far. And again, the corpus that we used is a combination of a couple of different corpuses and a small one. So we've already actually talked about this. But this already shows like a good proof of concept, and even more that this can be easily implemented over much bigger corpuses, and with capable models like 3 billion parameters or more, you would have much faster retrieval with almost no important metric degradation. So okay, we have talked about this concept, but this was kind of theoretical, but good thing is that we also exposed a Python package that you can just pip install and use right away. The couple of limitations, let me pull it right away. So in this case, we are using a specific vector database. When I say we, it's actually me. So for me, my time is limited, so I wouldn't go and implement for all the vector databases out there as connector to this pipeline. So for me, I just use Quadrant, for example. So what you can do, you can load your model, create your collection. That's in the naming of the database, right? And you can create your retrieval, and you can play around with different types of parameters, how you can pool. And it's actually, we talked about a couple of strategies, but there are a couple of different strategies given the model. And it's also open source. You can go and contribute. You can add, let's say, by the time of the study, there were X amount of good visual models, right? But maybe as of today, there are many new updates, so they can also be included in this package through some forks, community contributions. And at the end of the day, you can play around all these parameters. It's very easy to go and right away use, and you just provide your PDF, for example, as input. Under the hood, it will take screenshot of this PDF, do the cropping if you want. You can be also aggressive. There are different types of parameters. You can play around how aggressive you want this cropping to be. It can also have a connector to a public free data store for images. That's called Cloudinary. In this case, this is the integration that we have. So you will have all this resized image, cropped image, everything out there in case you want to go and investigate. So it will do all this processing, and using also the token cleanup that we have discussed. It's also implemented under the hood. It will do all this processing for you, push into your created data store, and then you can use it during the retrieval. So it's out there, you can use, and basically here are different links. There is Hugging Face repo also for people that don't want to write any code. There is a UI that you can upload your PDFs basically and work on them. But given that this is hosted on very cheap CPU, if you have big documents, that's the cost for you using it for free. This is the preprint if you are interested to read. As the conference will take place in around 2 weeks, it's not publicly available under the DOI link, so it's just a preprint. Anyways, these are the resources, and I guess we have done. Yeah, so this, I'm sorry, this is, by the way, just I will put it here. This is for my educational fundraising, so I just leave it there, and I'm ready for any questions you have regarding this presentation.
Thank you. I have one question about the storage of your mentioned visual RAG system. As I understand, the visual RAG system which you are created, the data of this RAG system consists only of images, right? My question is like this. Is it optimal or is it a good way to process image of a dog and image of a PDF which has text in it in the same way? Will that be, I don't know, good for a RAG system to get information tokenized? Because in the image of dog there is image and some patterns, and the screenshot of a PDF is text. So processing these two different types of images with two different types of information in it, is it a good way to do this in the same way? So
when you said a screenshot of a PDF is a text, what do you mean by that?
Screenshot of a PDF, like the information of that image is the text, which is sequential thing, and the information of a dog picture is just patterns which some models recognize as dog, classificate as dog, and the information or the token is showing like it is a dog. So is it a good way to process that two images and tokenize that two different types of images in the same way?
Let's put it this way. So a quick recap. When we talked about the bottleneck of the text processing pipeline, where you would have different types of layouts. I'm not sure how different is the PDF page versus the dog that you are mentioning, like what do you particularly mean by saying dog, but in general, anything performed over text has the bottleneck of capturing any charts, tables, pictures, anything that can be within it, while the visual one is like the most probably universal one that you can have, because independent of if you have a PDF page, if you have, I don't know, some other data source, if you have Excel document, whatever you have, in general, if you consider this abstraction where you have some data, you are looking into it, so you're reading based on your eyes, so you're seeing something, and it's kind of mimics how humans would do, like you read, so it takes a screenshot of whatever you have and process it using these vision transformers under the hood that we talked about, which, let me go to that slide, which just divides whatever you have as image input. And let's say image input is the screenshot. So you have a PDF page, as you said, like it's a text, right? Or something, text and markdown or whatever is under the hood. We take a screenshot of it and treat it as an image. And these models are capable of seeing everything. So independent of what type of data is that, this was the goal. Like to use a capable, high-performing visual model that will be able to extract any information. It's like a very universal abstraction over your input type. Charts, tables, whatever you have, it will provide the performance. I don't know, have I managed to answer to the question?
I have a question that has
Sure, go on.
Hello, thank you for your interesting topic. I have a more technical question about technical optimization. Did you hear something about TurboVec and page index optimization? TurboVec, it's apply Google TurboQuants to how we store vector index to allocate much less memory. And page index is just a logical retrieval reasoning engine which split your text to the logical parts, and maybe you think about something like combined to these techniques. For example, use TurboVec to store visual embeddings to fast search much more faster than Quadrant or Milvus or any other modern vector database. TurboVec, it's look like it's more cheaper for the memory allocation and more cheaper for the time to search. And this approach could be try to search visual parts of your documents, and page index could be used to reasoning during text reconstruction.
And so thanks for the next question. So about the page index, if I'm not mistaken, it's again a relative new thing, which instead of doing this regular vector databases, under the hood it constructs some knowledge graph-like thing and doesn't use traverse using vectors, but just like this hierarchical graph or stuff like that. It's totally different concept. So it's like another alternative. It's like you want to travel from Berlin to France, I don't know, or any other country. So you just take a bus, you can take a car, whatever. In our case, we are talking about we have a car, we want to use car, how to optimize this particular car. And in general, whatever you mentioned, like let's say the same page index, under the hood, how you construct your knowledge graph. Again, you do this processing where you would, I don't know, divide into some textual representations or stuff like that. And again, you might face the same issue of losing some information whenever you have visual components in your documents. While this approach is just about, hey, let's use the visual systems to not lose this information. So maybe they can be given the topology of your, I don't know, or the specifics of your data. One approach might be much better than the other. I guess so, because I don't think there's a universal thing of like, hey, page index is always better than this one or the other. Most of the time in machine learning, we don't have this, right? And about the turbo vector, what you said, if I'm not mistaken, it's around 2 months, right? The turbo vector, the turbo quant that Google just released, this, I don't know, very light way of quantization.
Released it in 2025, and it's just have more news because they try to achieve to the LLM inference, apply to an LLM inference, but turbo it's just apply turbo quants in different approach in different
To narrow down your precision, right? So instead of you using FP3216 or something like that, it just performs some, I don't know, optimal quantization. That's a consequence of which you are using low memory. But again, maybe they can be used in conjunction. We didn't have this study. So you have these vectors, independent of the dimension of the vectors. You have the same question. What's the data type that you store in? Maybe the same turbo vec can be applied over here. So in this example, if I'm not mistaken, the code, I have it. You can mention, in our case, we have the implementation for float 16 and float 32. What you are saying, you will even narrow it down. And whenever you halve the precision, you are getting almost like a linear time scale in your memory. So maybe whatever you are saying, maybe can be used in conjunction with what we have. It's like another axis. You can consider it's like we are doing this axis of optimization. You are suggesting an orthogonal one. I don't.
Thank you.
You too.
Thank you. I have another question that is similar to other questions. What you explained is that there are two stages, and the first stage we use a smaller model, a faster model. My suggestion, or I have this idea: why not use for the first stage or another at a third layer, and use something like a classifier for example, if you consider database sharding. When we are looking for a word that starts with A, if we've done sharding, we can just go look inside all the words that start with A. If you have classification, for example, a picture is a picture of like the dogs, the animals, and a picture is like a picture of text PDF. So if we only do the embedding search inside the text, it will be the amount of data will be less, so it will be faster. What do you think about using a classifier for the first stage instead of a small model?
One small note and one follow-up for your question. So in our in this two-stage pipeline, we are not using a simple model than a more complex model. We are just using a more compact representation of features. You can consider this way. The model, underlying, or everything is the same. It's just in the first stage we use the 32-dimensional representation. That's pooled representation. So it's actually a smaller set of features. You can consider this way. And in the second stage, we are using a more extensive set of features. There's the difference between the two stages. And about the classifier, I'm not sure I'm following up where this classifier comes at the inference time and what it classifies and how it helps. I'm not sure I'm following.
I mean, for example, when we have a query, we can classify that this query is a query of an animal, like between the classes that we have. And then we do the vector search inside the vector part of our database.
Interesting question, but it means, first of all, you will need to do, I don't know, some rigorous classification before data ingestion to have for each type of, I don't know, granular class. So in this case, you even would need to have very representative and differentiated classes. Like it's easy when you talk about dog and cat, but what if you have lots of documents about scientific researches? How are you gonna differentiate between pages of different papers to then sort them in different collections? So then your classifier would come to play and say, hey, this query is about turbo quant optimization, so that you can go and search over these particular pages. So if you manage to construct such a good classifier that independent of the input, because in your data store you can get any input, right? Any type of document, or let's say you have some niche, you have some domain. Anyways, you don't know in prior which kind of document will come, so you might have a new class that you don't have initially when you were storing your data store. So independent of you do sharding or whatever, it's just about how you differentiate these classes, which are most of the time in production you will have very much overlapping classes. Also, we are not talking about how strong classifier that should be. Maybe it will become your own bottleneck in this pipeline and will create latency. I'm not sure, but maybe it's a thing. Maybe if you have a very particular domain, like you are sure that you will only be exposed to particular set of classes during your queries, maybe that's a good approach to go with. As the saying goes, if you can do it simple, do it simple. If you need to kill a bird, you don't need a big vehicle to do it. You can just use a gun. So if you have a simple approach to solve it, that's the best way to do.
Thank you.
Thank you for your speech. I think your paper is really bright. I have several questions. First of all, about the benchmarks. I am really interested. What are we retrieving? Is it a page or chunk or image chunk? And the next question is, how do we find the page we found or chunk we found to answer the question of the user?
Okay. The first question the answer of your first question kind of already eliminates the second one. So in our case, chunk itself is an image. So we cannot, maybe we can retrieve a part of image, but it's difficult because whenever you have this type of processing, when you divide image into patches, like maybe your chunk, semantically, like how me and you would understand chunk, should be a paragraph. A paragraph in this case can be a set of, I don't know, these 10 patches or whatever, 12 patches. But in prior, we don't know that. So this technology, what it does, it retrieves the whole page. This is how the benchmark, this is how data sets are constructed. But at the end of the day, it's not a problem because current models, and especially, I don't know, many multimodal models that are even open source out there, are very good when you just provide to your LLMs as input the whole image as context, and they are pretty fine with that. So most of the cases, you don't even need to go even more granular, and within the image, extract a particular chunk. At least we didn't do this study, and this visual RAG concept itself was about retrieving images. So we used that same Vidore benchmark, and our retrieval was based on just retrieving the correct pages given the query.
Okay, cool. And one more question about chunking. I believe in some cases we could split the letters in half and lose some lines of information, some parts of text when we split in without overlapping.
Are we talking about cropping? Like which
No, not cropping. I mean, it's more about, it's more general question about image models, not about your specific paper.
You are saying that, I don't know, mid-here you can have some characters, as I understand,
Yes,
right?
yes, we split some character and we don't know, we lose the whole line of text because we split in between of these symbols.
I see. That's a wonderful question. And assuming that it was a problem, let's say, before even this study, so it would propagate to our case too. But The underlying, maybe it's an inductive bias reasoning, I don't know, but the underlying assumption is that, so if I were to write something in half, let's say this is the hello, right? And if I were to drop this part and ask you to read it, you might most probably infer that it's hello, right? You will do the extrapolation. I don't know if you have a, I don't know if you can read it, but I guess you can understand that it's about hello. And the way that these models are trained, they also saw many patterns like this. And probably the underlying explanation of why this is still working good, though it can split in half, is that they can just extrapolate like you do. Like even if I were to put a wrong letter here, or whatever, I don't know, even 2 letters, you would most probably guess that this should be hello. So same thing applies to them. Most probably, but I don't have written down scientific explanation on that. This is just based on the experience that I have.
Okay, I see, thank you. And one more question, please, about vectors that we can split in the middle and lose not all the information. It's like
very small
PCA or
part of
something.
information. This is how they are specifically trained.
So it's not whole language models, not for all the models.
Yeah,
it's
these are
for
specifically
specific ones.
Imagine they are trained in a way that they have, in your regular models that you try to, given the input, provide an embedding, what you do in your loss function, you most likely use some, I don't know, contrastive learning or stuff like that. When you try to, for similar items, you try to maximize their similarity, and for different items, let's say you have 2 different set of images, you want their embeddings to be far away. And in this case, they, during this simple loss function, they do actually 4 loss functions. So they train that same loss, that they kind of enforce the model to be able to do the same idea of closer items, semantically meaningful things to be closer together in embedding space for all these 4 size of vectors. So this is during training time, they are combining 4 different loss functions. So for loss functions actually not different. They are same loss functions, but operate on 4 different embeddings. So the model provides 4 outputs.
We have time for the last question, then we have a pizza there, and we can move there. And
This is called Matryoshka. I highly suggest you go and read their work. And if I'm not mistaken, it's currently used in OpenAI. Like in GPT-5 series of models, they have under the hood also using, at some cases, for their embedding models or stuff like that, they have the Matryoshka under the hood.
Does anything change when the text, the PDF, is in a different language in this system?
Yeah, so whenever we're talking about visual models, this visual Colquhoun or other set of models, we very shortly mentioned that these are actually multimodal most of the time. So they are their own text encoder and visual encoder. And depending on how these models were trained, so if they were exposed to other set of languages, whether in their visual data, like images, and the same with the text, they will probably handle this because there are also many multi-language models. But in particular, I'm not sure about these particular models that we have talked. I haven't looked into their capability of reasoning over other languages. But there will be plenty of models that are both multimodal and multi-language that you just don't even need to worry about it. They are under the hood, they are pre-trained in a way that will recognize other languages too. It's just a choice of a model.
Thank you.